Hey everyone, this is Dr. Walker. In this video 519, we're going to find the potential energy of point charges. This is somewhat of a continuation of the previous video where we found the change in potential energy of a charge as it moved in an electric field. So the first thing we want to do to consider this is to look again at a mass. If we consider a ground level to be 0, then we say that a mass has no gravitational potential energy. And if we want it to have some gravitational potential energy when it has some height, that means that we need to apply some kind of external force to lift it to that height, thereby giving it that energy. So let's look at the charges the same way. There's a positive charge Q here, and let's say we have a positive test charge really far away. My paper doesn't go too far, but let's assume that this positive test charge, which we'll call Q naught, is really far away from this fixed charge over here. So if we want to bring it to point P, then there has to be some kind of external force that is doing some work to bring it there, because it definitely doesn't want to go there. That external work to bring it there is going to equal the potential energy of the system of charges. We don't just say that the test charge Q has potential energy, we say that the system of the two charges have energy, since this charge Q wouldn't have any energy without this one. With that being said, let's find a work to bring a positive test charge Q naught from infinity to point P. So that external work that's going to be required is going to be the integral of the force dot dr, we can call it dr, so along the r direction here. And we're going to bring it from infinity all the way to point P, and let's say that point P here is a distance capital R from the charge Q. Now, the force that we have to exert to bring the charge here just has to oppose or balance the electric force that is pointing away. We know that there's an electric force pointing in the same direction as the field, in the R direction. So what we can do is we can say that the external force is going to equal the electric force, but since it's in the opposite direction, we can just flip the limits of integration. So we're going to have Fe dot dr. And now we can go ahead and write this. The electric force is equal to Q naught over R squared. It's in the R direction, R hat, dot dr. Very similar to the guided example 518.2 that we just looked at. So now the R and the dr are in the same direction. So the dot product cancels out, and we're left with the integral here of 1 over r squared, because we can take out the Q naught. So we have the integral of 1 over r squared, which is equal to negative 1 over r. We can go ahead and do that integral, and it's going to be from r to infinity. When we plug all of this in, we're going to get negative 1 over infinity. We're going to get 0 minus a negative 1 over r. So 0 plus a 1 over r. So we're going to get Q naught, and then 0 plus 1 over r is just 1 over r. So all of this is going to be over r. So this is the external work required to bring these two charges together. And we said that the electric potential energy of this system of two charges is equal to this external work. So if we just want to call the charges Q1 and Q2 instead, and then instead of writing Coulomb's constant, we can write it in terms of permittivity of free space. So Ke is 1 over 4 pi epsilon naught. And then we can say that we can go back and call it little r, where little r is going to be the distance between those two charges. So this is the general expression for the potential energy. I did make a note here that if the charges are of opposite types, the potential energy is negative. You can see here, if you multiply a positive and a negative, then you will have a negative energy. So it makes sense that if you have a positive charge that you're bringing here, you're doing positive work to bring it here, you're giving them potential energy, so we have that positive potential energy. If we have a negative potential energy, then that means that you actually are doing work to take the charges apart, doing positive work to take the charges apart, versus doing positive work to bring the charges together. So that's just a sign convention for the potential energy. We can expand our definition to a system of 3 charges or even a system of n charges. In this picture, we have 3 charges, so we can look at the potential energy of 3 charges. And basically what we do, since potential energy is scalar, we just add up all of the potential energies. We know that Q1 and Q2 have energy, Q2 and Q3 have energy, and Q1 and Q3 have energy. So we have to add up those 3 energies. The expression is Ke times Q1, Q2 over R, or it would be R12, and then you just do Q1 and Q3 over R13, and Q2 and Q3 over R23. So that would be for the 3 charges, and now we can expand it to n charges. We can just write it as a summation. We can sum all the i's and j's from 1 all the way up to n with n charges, and it's going to be qi and qj and rij. Now we don't want to double count the subscripts since q1 and times q2 is the same as q2 times q1. We don't want to double count all those energies, so we can just write for I less than j to make sure we don't double count. Another way is to just leave it like this, but then divide the whole thing by 2 to make sure that you don't double count. So that is it. We finally found the potential energy of a system of charges, and now in the next video we will do an example.